going to speak today about is how to operationalize machine learning, or how to build machine learning which is ready for production. So we'll start with some of the challenges, and then we'll share the architecture that we've been promoting based on some open source tools. And I'll finalize with a bunch of demos in machine learning and deep learning, depending on how much time we'll have left. So let's start with that. So first, let's understand the challenge. So most organizations today, you build models, you do it in an interactive way. We're going to look at it from a different perspective in a second. You're building the models, you're creating a nice endpoint, but really the big challenge is creating machine learning models that fit into business applications. And those business applications usually exist with live data that comes from real sources. Those need to react and inject events into real systems and respond to users and so on. So building the operational pipeline is usually a makeover. Usually whatever you build in the development environment with your notebooks or PyCharm environment is not the same code that is used in production because of aspects of resiliency and scale and security and so on. So we're going to look into how to build platforms that are more continuous, where a lot of that overhead doesn't exist. And again, why do we need to do it? Because in many cases, people that haven't done this exercise of productizing the machine learning think that, you know what, you can just go and develop something in Jupyter and test it, and it will automatically go into production. It just doesn't work. In production, we have services that needs to be always on. They need to address SLA and performance. They need to be secure. They need to be resilient. So whatever you built in your notebook is not necessarily the end game. And this refactoring exercise of taking whatever the data scientist did and factoring it into a production application is a very, very costly exercise. And why is that? Again, because if we're looking into the flow, usually when we're in a research mindset of developing a model, this is what we do. We essentially grab some data from a data lake, a data warehouse, an object store, and so on. We extract it, we put it in our notebooks or a development environment. We do some interactive data preparation. Usually it's small scale, because if it's very large data, it's going to take ages and exhaust our Jupyter memory. So we'll work around the data, we'll do some aggregates, we'll identify patterns, we'll generate features, and then we'll do some training, and we'll build a model, maybe using some automated cloud service. Once we build a model, we may want to evaluate it against different patterns, make sure not only that it's correct and accurate, but also that it may be resilient and compliant and so on. And this is usually an interactive exercise of developers. But when we move into production, it doesn't look like that at all. It looks more like that. Okay. And why is that? Because we don't just train interactively on our notebooks. We need to train our models on live data, which comes from production systems. That training happens to work within microservices or containers in an automated workflow engine. So we need to build the same thing that we've built in development. We need to build it in production in a more containerized and microservice-oriented way. It needs to be resilient. It needs to be monitored and tracked. But this is just one piece of the puzzle, the training aspects or the development aspects. Once we build the model, we need to serve the model. And just building an endpoint behind some HTTP address is not building a serving application, because that application usually interact with some real user or consumer or API. We need to transform those APIs. We need to enrich, for example, on getting some customer identifier, I need to enrich it with all sorts of customer features, and only then do the serving. And once I've made the prediction, what do I do then? I need to create some action. I need to push the results into a database or invoke some push notification to a user. This is an application that doesn't end in like an endpoint. And beyond that, you have the monitoring aspects of monitoring the data for compliance, for anomalies, for drift, monitoring the accuracy of the models, monitoring the health of the systems. So it requires telemetry into all those systems that we develop and build. And everything really starts with the data. So before we even start the training or serving pipelines, we have to build the data in a way that it meets the needs of our models for training and serving. So on one end, sort of batch access, on the other one, real-time access. Every time we want to retrain the models, we need to be able to grab a snapshot of the production data. No one is going to send it over with email or some sort of pre-cooked CSV file. It all needs to be automated. And let's assume we're building a new version of our models or our serving pipelines. Everything here needs to be synchronized. We can't just train a model and use yesterday's data. We need to use data with the schema that our model expects, both in the training and the serving and the data. So everything needs to be versioned as a whole. Everything needs to be developed as a whole. And organizations that treat all those different parts as silos, and then everything moves in sort of manual channels, essentially fail. This is what we've seen with organization which look at it as a task of all the team, the data engineers, the data scientists, the DevOps, etc. They're usually the ones that succeed better. But we do need to simplify this entire process, that we can really deliver production applications in a much simpler way. And this is really where when you build an application, it's not just about writing some code and running it in production. There are so many things that need to happen from the minute you wrote code, whether it's a data preparation code, a model training code, a serving code, API glue logic code, and so on. We need to take each part of that code. We need to package it. We need to containerize it. We need to address scalability. Not, sometimes we handle large amounts of data. We need to be able to scale horizontally those workloads and maybe performance units. So things that we do in an interactive fashion and querying a database, we probably can't query a database 1,000 times a second every time an event arrives to our application. And maybe we need to apply caching techniques and parallelism techniques, or even use GPUs or accelerators to be able to do the workload in a way that it fits production. And finally, we have to instrument everything that we're doing. We have to be able to monitor and log the activities and control the security and access control and version everything that we do. And also, we want to apply automation. Every time we change the code, we change the data, we want to have a fully automated pipeline that builds our model or build the different production artifacts, functions and code and containers and so on. And when we build a new thing and we have an application that's already working, we can't just like substitute all services with the new services. We need to be able to do things like rolling upgrades or even do A/B testing, test our new model in some test environment, verify that it's working with a bunch of customers, and then only promote it to production. So what everyone sees today is that really developing something in a basic fashion, the POC level, may take weeks, but building a production application that takes into consideration all those things that I mentioned could take more than a year, and that's according to all analysts. And depends obviously how engineering-oriented the organization is, but it does consume lots of resources and lots of time. So what we're trying to think is, okay, what if we can reverse everything? Instead of thinking research first, we're going to start with our notebooks and build some model, and then someone is going to refactor all the work and build it using Java or Spark or whatever into production. Why can't we think first, what do we need in production? How would the production pipeline look like in a modular fashion where we can upgrade different components at a time? And then how do we reach that point where everything just falls into those Lego building blocks? So after working with lots of customers on production solutions, some of them are real time, some of them are very high performance and very high throughput, we understood that essentially we need to segment the problem to 4 pieces. Okay, the first part is how do we generate data that will later on be used in the training, the serving, the monitoring. So that's where the concept of feature store comes into play, and there are few feature stores today in the market. And the other part is how do we automatically build the models, not manually, using an interactive fashion. Maybe we start in an interactive fashion and then, somehow seamlessly move from this interactive workflow into something automated, which essentially knows how to grab production data snapshot, run the training, run the testing, validation. Once it's all working, put it up to promote it to production or to staging. So this is where we call it machine learning CI/CD pipelines. Once we go into production, again, it's not only serving an endpoint, and we're going to look into a few demos from 3 different applications. We're going to look into like a fraud application, a deep learning application with images, and also an NLP problem. In each one of those applications, there's a complete pipeline, anywhere from intercepting API calls to enriching data to processing to monitoring anomalies and so on. So these are full pipelines that need to be addressed. Sometimes today, the data scientists are not aware of the challenge because they're saying, okay, you know what, I'm delivering a model endpoint, and someone else is going to own the problem of how to take that model endpoint and deliver that as an application to the business that someone sometimes doesn't even, you don't find him, and the product just gets stuck because no one has the engineering resources to build that. So we need to look at it into it in a more holistic fashion, and we'll see that in the demos. Now, as we build those pipelines and now we to intercept information and build features and serve and monitor and all of that data needs to go back into a telemetry system that sees all the picture, not just the serving. It has to understand how the training was done, what was the data used for training, what are the statistical behaviors of each features, so it can compare and contrast all of those data points and build a picture of, okay, my model is misbehaving, there are anomalies, maybe it's drifting, maybe the data patterns that I'm getting in production sorry, are not similar to the data patterns I've seen in training. So how can I do that if I don't have access to the training data and the serving telemetry and all of that? So what you see here is that we have to have an integrated solution. You can build that integrated solution yourself by just picking up different tools and gluing them together. You'll find that you end up building lots of glue. What we've done in Equasio is essentially developing a set of open source packages and frameworks. MLRun is the leading one in those, which know how to orchestrate the different open source and cloud services that deliver those point solutions into a more comprehensive architecture where all those things are glueless and can allow you to build those pipelines in a matter of weeks and not months or more. So this is the general idea. And the way that they would integrate with all the rest of the tools out there is through simple APIs and abstractions. And we're going to see how it all falls into place. So the general idea, if you build today your solution, where you go, you build some code, and then you let some MLOps guy or DevOps guy or ML engineer, depending how you call them in your organization, refactor the entire set of work into YAMLs and Kubernetes and Jenkins and all that. That's a lot of work. So that's something you do today manually. And then once you build those individual steps or individual things, model serving, data preparation, and so on, and you want to build a pipeline, then comes another team that needs to take all those different individual building blocks and build more of a workflow or a pipeline out of them. Pipelines for training and development, as well as pipelines for the production. And now that you've built all that, you're trying to monitor, but because all of those are discrete pieces with nothing in common, how do you really monitor higher level information like accuracy of a model or behavior of your data, what kind of features are misbehaving and so on, if you're only monitoring low level stuff? So then either you build a lot of glue to do that, but also those systems don't have a feedback. You can't just automatically retrain or automatically go and update the features based on valuable data. So the approach that we've taken with MLRun, which is again open source tool, is to automatically all those different steps. So take the code, and there's essentially a method called code to function. It automatically turns your code into a microservice function, a fully managed, fully elastic microservice function. And then once you build those functions, you could just compose them into bigger workflows that will run automatically in your CI systems or running over Kubeflow or other automated workflow engine. But you don't need to redevelop anything. You just take those Lego building blocks and stitch them together, along with pre-baked building blocks that are part of a library. And all of those building blocks have built-in telemetry, so you don't need to write any additional code. Every building block that you're using, whether it's running a training or experiment, will do experiment tracking. Whether it's a serving function, it will track all the data going in and out and analyze the accuracy of the model. All those things are glueless and codeless. And because you have so much telemetry, you can use that for a feedback loop, whether it's to retrain models based on a snapshot of data, or whether it's to get the data scientists. One thing that I've seen a lot of data science really wish for is have access to production data, so they know that those features actually work or don't work. And this is really what is allowed here. There's a feedback loop where all the production data goes back into the feature store and is accessible, again, obviously, if they have the permission, to the data scientists to examine how their models really behaved in production. And this is all powered by a concept of serverless. You've probably heard about it, but instead of you building code and containers and all of that, you have a piece of code, you throw it away to an engine. That engine builds that service for you, and it makes it elastic, auto-scaling, and it has built-in telemetry and resiliency, knows how to recover from failures and all of those. This is really the trend of moving from containers to a concept of serverless function, and that's being used extensively in MLRun. The fact that we're building microservices automatically means that we can also instrument them and sandbox them automatically. So we can build a sandbox around every code that is getting delivered to production to automatically track what is going on, what's getting in, what are the parameters, what is the data going in, inject credentials to make sure things are secure. And once the job or service is running, we can automatically track all its outputs, its results, its operational data like logs, monitoring, telemetry data. So out of that, we can actually build maps of like lineage data, which data was used in training and where did it come from? Because we track all the different executions, we can build a map automatically of how data, parameters, everything flows in the system, and automatically track experiments and other aspects. So again, in MLRun, we have 4 key categories that are addressing the 4 pains in operational pipelines. So the first one is the feature store, which is really about how to automatically build features for production and for training and for serving. And we're going to see how it works in a second. The second technology is essentially real-time pipelines that know how to essentially take them all, take business logic, take the feature store aspects of real-time analytics, and stitch together a full pipeline with telemetry and monitoring and all of that. There is a component of full model monitoring and pipeline monitoring. So it's not just for model accuracy, but you can put other custom business logic there, anomalies, and there are things in deep learning that are more interesting. We won't dive into them. And also we're looking for a full CI/CD, a full automated flow of how every time I change the data or I change a code or I issue a trigger, we want everything to happen automatically all the way to a deployed system, and do rolling upgrades and all those aspects of automating the flow of deployment stuff. So those are the 4 key categories that you'll see in MLRun. And the first one is about the feature store, which is, again, an analytics pipeline that know how to connect to a variety of data sources. The first thing it does is essentially knows how to connect to them securely. Then it knows how to build transformation pipelines. We're going to look into that, how we're transforming data, whether it's real-time data or batch data or continuously ingested data from external databases. We want to transform them into meaningful features, things that have like aggregates and joins and all that, and one-of-them codings, all things that turn a raw data into a feature. We take all those features, we catalog them in a full catalog that you can just build applications off of them, and we serve them to different applications. So we can serve them through standard tools and APIs like Spark APIs or through JDBC to PI tools. They can work interactively against pandas or Spark data frames. You can use them in the training, so you can essentially create a snapshot of data from production data, run it into training. You can even store that snapshot for later traceability, so you know how you train the model and based on what exact data. You can use that data for serving in real time. And also the same data is used for model monitoring. It's used in two ways. One is what is model monitoring? Essentially, we're comparing the production data with sort of the historical data or the trained data to see that there is a match between both. It's more of a statistical analysis. So this statistical analysis is automatically stored in the feature store. So the model monitoring pieces are grabbing the statistical analysis results and they're contrasting it with the production data, and based on that, they're generating alerts. They're also rewriting the production data into the feature store. So if someone like a data scientist wants to see the data from yesterday or from now, it just opens a notebook and views that and uses that as just yet another data frame in the system. So this is the concept of a feature store. We're going to see that in action in a couple of minutes. And this is essentially how it works. You build a transformation pipeline. We're going to see that done through the SDK in a minute. Once you build transformation pipeline, it brings all the data as features with all their statistics, their schema, everything is getting analyzed immediately. And once you have those features, you can just select which features you want to drive into a model and then run the training, create a snapshot of the data, run the training, or use those features in a real-time application. There are also advanced features in those APIs, like auto imputing and filling missing data and all that based on statistical analysis. So things that you usually work pretty hard on and are built into the functionality. So that's the first part of essentially building the features. Now that we have features, we need to build a model. The model usually is not just doing training. We may want to do training, then we want to do validation and testing. In many cases, you could do further optimization. In machine learning, you could reduce the dimensionality, reduce the amount of features by examining which features have bigger impact. In deep learning, you could compress the layers, and in those cases, will lead to better performance and potentially better accuracy. So once we've tested and validated, we'll build optimizations, and finally, we deploy the entire pipeline, not just the model serving function, but also the model serving with the real-time features and potentially other transformations, as we'll see in a minute. The next part, as we discussed, is essentially deploying a serverless pipeline, which comprises of multiple steps. And there are examples that we have that are like 50 steps long, especially in NLP applications. I'll show a simple one. But again, you have to integrate with APIs. You need to do a set of transformations. You need to do enrichment. You need to serve models. Sometimes you serve multiple models using ensembles or other compositions. And finally, you need to react and push some data into some database or push some notifications. So this requires a lot of coding. It's not just the model serving part. And this is a built-in part in MLRun. Essentially, how does it work? You compose a graph. We'll see that in a second. Using very basic Python class coding, that graph that you assemble could actually be distributed across multiple processing engines with GPU, without GPU. For example, the serving part could be with GPU. The processing part could be without GPUs. You can compose it. It's using streaming between those compute engines, and essentially builds everything automatically for you. Builds a full pipeline, real time. Everything is auto scaling horizontally and vertically. Everything is fully resilient, full monitoring and telemetry, and so on. So this is, by the way, there was a great session from IHS Markit yesterday showing their NLP pipelines and how they're using that technology to scale to enormous, parsing enormous amounts of documents using that technology. And finally, when we build everything, we want to generate telemetry. We want to essentially collect every telemetry data from every serving function, from every model, and compare it with the expected result. So we can, these are just snapshots where you can actually see, you can dive into real-time features. You can see what is the actual feature values now on that specific model. So that's providing great visibility. And again, you could also grab all the data as pandas data frames and play around with that on your notebook. So with that, I hope I didn't run too fast, but I want to try and get to a few demos. So we'll look into three demos, 2 or 3, depending how much time we'll have. The first one is a machine learning demo, which is a real-time fraud prevention or detection. So if you think about fraud applications like credit card fraud, we have transactional data, like people swipe cards, and every time they swipe the card, there is a transaction. There's other auxiliary data like account activities, logging into the application, logging out, changing passwords, etc. That could give us indications of someone potentially committing fraud. There may be other static data like user records, where does he live, zip code, can give us indication on social economical information and so on. All those features need to essentially go into the feature store, sell them in real time, like the real card transactions will go in real time. So they need a real-time serverless engine to essentially process the Kafka streams, aggregate, and so on, and write the features into a feature store. In some cases, it's just batch, like reading a table from a database and then writing them into the feature store. We have such applications, by the way, with about 70 of those, 70, which generate about 10,000 features for an individual application to do, very accurate decisions. Once it's in the feature store, we can just interactively explore the data. And every time we want to run training, we essentially grab a snapshot from the feature store of those features that we need. We do all sorts of feature optimization work on them, run AutoML, deploy them into a real-time pipeline. We can run the AutoML using Kubeflow, which is an open source framework. We also support SageMaker, Azure ML, and other frameworks. So you can essentially snapshot the data, throw it into a cloud service for training, grab back the model. Once you have the model, we essentially build the real-time pipeline using that model and the features in the feature store, and that serving application also generates the telemetry data, which goes back into the feature store. So if we want to retrain the model, we'll just retrain. So that's the first application that we'll see. But all of those things are in Git, so all those demos, you can access them later on. The second application is a deep learning application. So how to build a model? Let's assume we have a factory. This is based on a real scenario. A factory that has tons of images coming from manufacturing, and we need to detect defects in parts and so on. So the first thing that we do, we need to throw all those images into an object store or a file system. We may want to index the metadata of the images as well in a key value database, and also potentially write information into a queue. Once we have all the data landed in some object or file storage, we're running training. Because it's large amount of pictures, we have to use GPUs. We need to scale out horizontally. And then once we've built the model training using Horgot, we do two things. One is to validate and test the model, but in parallel, we're running optimizers using Onyx, if you know what it is. And that Onyx model is then going into the deployment pipeline. Everyone now thinks, okay, we're done. No, we just started, because the production pipeline is not really about running TensorFlow endpoint. The production pipeline requires notifications from the streaming engine, which need to fetch the images from the object store and run a set of transformation on those images, like resizing them, changing colors, and so on. And then only then we want to classify the images using GPU. It would be a waste of money if we throw all that logic into a GPU server. We'd rather have one container doing this, another container doing that with GPUs, and maybe some of the other tasks will be done on a separate container, which involves writing masks and pushing results into a database and indexing systems and so on. So, model serving is just a small portion of this entire application, as you can see here. And we could look into another third application, also part of the demos of NLP processing. There are two examples of NLP processing. I may show the first and simpler one. But again, we may want to, if we want to process NLP data, we need to fetch the articles. We need to summarize. We need to extract keyword. All of those steps are individual steps. and only one of them may run a BERT model for serving. All the other steps requires different manipulations. And sometimes there's like approximate neighbor searches, ANN searches, and many other tasks. You'll find that some of those pipelines may be 20, 30, 50 steps long. So with that, let's move into some demos. So this is a Jupyter notebook on our managed platform, but it's all that data we have is either in MLRun documentation. Some of it is here, like this demo I'm going to show you. The fraud detection is here, the same notebooks that I'm going to share. There are also a bunch of tutorials, but there are more comprehensive demos in the demos repository. The like news articles and mask detection that I'm going to show are also, all the code is here. Okay, so if you want to later on follow them, and you can shoot me a note through Slack or LinkedIn, and I'll send you links to those. So let's again take this pipeline that we discussed. Think about how much data engineering we need, and analytics, and Spark folks, and all of that. Look at how many features we need to generate, and the complexity. We need to build take this raw data set of credit card transactions, and we need to do all sorts of manipulations. We need to extract the hour of day, day of week. We need to do mappings based on ages. We need to do one-hot encoding to categories, shoes versus food, and so on. We need to build aggregates on the amount of transactional data. We need to build aggregates on like how many shoes you bought, or how much are you going to the groceries, and so on. So there are many different analytic manipulations that need to be done. You know what? You can try and do that in SQL. That's going to be pretty long, but then you're going to throw everything away for the production, because you can't really use SQL queries for production. So we'll come with a different approach. We're going to build a feature set, which is a collection of features that essentially all feed from the same source. In this case, it's a Kafka stream. And we're just describing our pipelines. That pipeline has data extraction and value mapping and one-hot encoding and some couple of aggregates. And that's it. That's my pipeline. It took me about 20 lines of code to build this pipeline. Something a data engineer will debug about 3 months. And then I could just throw some sample data into it, and I see my feature, all my features with aggregations and one-hot encodings and everything. The beauty of that is not just in my notebook. In one click, I'll show you in a second, it's going to be production real-time function that listens on Kafka. So I can go and debug my code and build the features. I don't like the features. I change a piece of code. I introduce my own custom Python classes and build it again, and until I'm satisfied. But that's something you can do interactively on your notebook. And then I would build other features. This is like the user the account features, even labels. I need to build the labels for the prediction. So there's another pipeline for building labels only for offline. I don't need real-time labels. And at a certain point, someone else, MLOps or DevOps, want to take the analytic works that I did, want to examine it, and he wants to deploy it into production. So I save this feature set. When I save the feature set, it's actually stored in MLRun. So I don't, I essentially have a feature set with usage information. I can see the pipeline that I created, and how it works. I can see the features that were generated due to my logic, even the statistical behavior of those features, preview of the features, and all sorts of things. And I see that for all the different features without doing anything. I just did my work on the notebook, and it all got there automatically. When I want to build it into production, the only thing I need to do is just say, take that feature set, take some runtime configuration like image that I'm going to use, and some other runtime considerations. Maybe I want GPUs and so on. Deploy ingestion service. This will automatically build a pipeline with containers that will go and listen on Kafka. Okay, so everything is done fully automated, and I could do it for the different pipelines. Now I build all those features. I have those production features fed automatically. And now let's run some training. So in order to run the training, I first need to decide which features I want. So I create a new, I log into my project, and I define that these are the features that I want. I want some features from the transaction feed. I want features from the event. I may want also the label, obviously. So I build a feature vector, which take all those features plus the labels. And I just want to materialize that feature set. So essentially, something in the background is going to do joins and as joins, stitch everything based on timestamps, etc., and build a feature vector for my training. And you just want to look at the feature vector. You're getting the feature. The feature vector is a pandas data frame or a Spark data frame, and you can just go and see the joint data with all those aggregates and one of the encodings and everything. And everything is joined from the different feature sets. And then I want to run a job of training. I'm just loading an MLRun pre-baked function from a marketplace. MLRun has a marketplace of functions that you could use. So I'm just grabbing the training function. I'm using a scikit-learn classification function, which essentially does AutoML. It can take a bunch of algorithms and run different permutations of my model and eventually generate the model object. So this generates a model. It reports the accuracy and everything. If I want to see that all those jobs running in MLRun, I go to open. I just open the dashboard. I can look into the training job and all the information that I gathered in the training job. What was the data used? What are the different artifacts that were generated? What are the results for different permutations of my hyperparameter search, and so on. So all of that, I ran it on the notebook, but it gets logged in the UI. And you could do it the other way around. You could run it in the UI and then track it from the notebook. But it's not enough. I have too many features. I want to optimize my model, so I can just grab a function from the function marketplace, which does feature optimization. I'm feeding it with the feature vector, and I want it to generate a new compressed feature vector. So it will run, and eventually it will tell me, see those 5 features, they will generate the same accuracy as those 30 other features that I generated before. Obviously, it's much better. My serving function will run much faster. So I'm just building a new model using that reduced set of features. Again, just rerunning the training with a reduced set of features with sort of the short vector. And in order to deploy that to production, again, I don't need to do much. I can go and build a serving function, or I could just use a library serving function. This one is an example of building your own serving function, which has a load and a predict handlers. It just loads the model, and then every time there is a prediction, it will inject, it will do the prediction. But those model serving steps, they're just step in a bigger pipeline, because model serving is nice, but I need to get the features, I need to do some actions. Maybe I actually want to build an ensemble across multiple models. So what I need to build is a graph, is a topology where those model servers are just pieces in the graph. And there's also sort of here something we call an enrichment voting ensemble router, which what it does, it automatically, you give it the name of the feature vector, you give it imputing policy, essentially substitute every non-value with the mean value, and it will automatically go every time there is an event coming from the user. It will essentially do enrichment. We will go to the feature vector. Let's assume you have a user ID or a credit card holder ID or transaction ID. It will build the entire feature vector from that key. It will drive it into 3 different models, because that's what I've defined here, and will run the average on those models and build an ensemble. And I could build a much more sophisticated pipeline, but just for sake of example, I build a very complex solution here in 3, 4, maybe 10 lines of code. When it's ready, I want to really see that it's working, so I can just build a simulator and throw some sample data into my simulator and see that it actually works. I did here something on purpose. I added a print here just to show you that this thing gets called 3 times, and also I'm printing out the input for the serving function. You can see that I just gave it the sample ID. I just gave it the sort of credit card holder ID, but actually the inferencing function got 4 values. So those are imputed values for those 5 values. Those are imputed values for all the 5 features that are required, and they're being thrown at the model. So all of that happened automatically. I won't dive through the rest, but in order to deploy that into production with full model monitoring and tracking and accuracy and all of that, I just turn on the tracking, I do deploy, that builds a full real-time pipeline in production, and I could test against the real-time pipeline. So you can see how I build a project that would take usually months. You could build it in less than a week with some help, and then maybe the next project you'll do without help because you'll figure out how this thing works. And again, there's lots of documentation for that. I don't have a lot of time to cover the other use cases, just to show you that it's not sort of a single trick pony for machine learning. There's a great example on deep learning showing how you can take TensorFlow or PyTorch, and you can just take TensorFlow and run it in the notebook without any instrumentation, without adding a single line of code that talks about scalability, checkpointing, logging, nothing. The only thing that you do in your code is add the single line, which is a sort of apply MLRun, and once you do it, it will automatically add auto scaling, horizontal scaling, containerization, GPU support, checkpointing, logging into TensorBoard, logging into MLRun, and so on. So all that will be done automatically. So once I took that code, I won't run through the entire demo, but you can look into that later in the Git. I can just take my code, convert it into a microservice function, provide it some storage resources, and then just run it with a set of parameters. This time I'm saying local equal false, which means run it in my notebook. But let's assume I want to run it with GPUs. I just rerun it again. This time I don't turn off this local flag. If you know, Kubernetes is essentially generating and automatically pods on Kubernetes, which execute my workload. And if I want to run at bigger scale, horizontally scale my workload, I just again change a flag and say use GPUs, use multiple replicas, just some configuration, and rerun the job. It will now run on two nodes with GPUs and everything. I don't touch my code. All the instrumentation is happening automatically. And again, all the other things we talked about serving. There's a serving pipeline here with image processing, and the classification is just one step of the pipeline. Composing all that pipeline is essentially those 4 lines of code. And there's also an example of a fully automated pipeline, as we discussed before, with the Onyx optimization, etc. How we compose this automated pipeline, which does all those different steps as a graph, essentially preparing the data, the images, running the training, building them all, running Onyx to compress them all, and then deploying the full production pipeline, which is comprised of about 6-7 individual steps. And later on, you could look into the news article demo. Again, it's in the same place. Also, pretty cool demo of how it injects data from a news service and essentially builds a table with the results for every document, all the classification information. Again, using a very simple flow. So with those demos, I encourage you guys to go into MLRun. There's a lot of content in the documentation. There are lots of different demos that show the usage. And if you have any further questions, just contact me over LinkedIn, and we'll be happy to address your questions. So I see we have a bunch of